Hello, everyone. Welcome to the HPL seminar this week. I am pleased to introduce today's speaker, Ashna Subramanium. Ashna started her undergraduate in 2015 here at the University of Calgary in kinesiology. During her undergraduate, she found herself interested in the field of biomechanics, especially when she was a research assistant working with Dr. Art Kuo in 2018 and Dr. Ben O'Nick in 2019. At that time, she primarily worked on the effects of shoe upper construction on lateral shuffle movements, which is today's topic. After she achieved Bachelor of Science degree in 2020 last year, she started master's course under the supervision of Dr. Ben O'Nick and co-supervision of Dr. Walter Herzog. Ashna has been primarily interested in understanding how different footwear would contribute to athletic performance. So currently, for her thesis topic, she's been working on how to quantify the teeter-totter effects in shoes with the curved carbon fiber plates. And also she's been trying to do the fast track PhD. Aside from her academic career, she also introduced herself as a tennis player, and she was part of the Dinos tennis team at the University of Calgary. She also wanted to introduce one of her best friends, a 15-year-old dog named Simba, who shares lots of memories with Ashna for a long, long time. Today, Ashna is giving a talk entitled Effects of Shoe Upper Construction on Lateral Shuffle Movements. Whenever you're ready.
Thank you, Sangwan. I'm just going to start sharing my screen here.
Yep.
See?
Yep, I see your screen.
Thank you. So from previous years of footwear research, we know that modifying footwear features affects lower limb biomechanics during locomotor tasks. And as an example, a shoe feature that has been studied often in research is the midsole bending stiffness. Studies have shown that increasing the midsole bending stiffness of shoes results in decreased mechanical power at the MTP joint during running. Another shoe feature that has been shown to affect lower limb biomechanics is the heel to toe drop. And a study done in 2019 showed that changing the heel to toe drop affects knee and ankle moments, as well as vertical loading rates during running. Now, these are just two examples of many shoe features that can affect lower limb biomechanics and thereby affect performance in locomotor tasks. A study done by Hukamer and colleagues in 2018 that compared a Nike prototype shoe to two other shoes, the Nike Streak and the Adidas Boost, is a perfect example of how modifying shoe features affects running biomechanics and performance. The prototype here differs in many aspects from traditional running shoes, in that it has a drastic toe spring, it also has a thick, compliant foam midsole, and an embedded carbon fiber plate in the midsole. Now, this prototype is popularly known as the Nike Vaporfly shoe, and it is best known for improving running economy by 4%. The follow-up study by the same team in 2019 examined lower limb biomechanics in the same three shoes. And one of their outcome variables that they used to quantify the biomechanical changes was the ankle joint power and work. They found that positive and negative joint work, which is defined as the area under the power curve here, was significantly lower in the Nike Vaporfly shoe compared to the other two shoes. And if we go back and look at the three distinct features of this shoe, we notice that all three, the drastic toe spring, the thick compliant midsole, and the embedded carbon fiber plate, are all related to the sole of the shoe. Now, this is not just true for this study, it is the case for most footwear research. A literature review done by some members of the NIG lab summarized the results of studies that investigated systematically changing footwear features on lower limb biomechanics. And if we look at some of the high-level results of this study, it is interesting to see that out of the 68 articles that were included, 46 of them investigated the effects of midsole and midsole-related modifications. Only 7 of the studies actually investigated the effects of shoe uppers, which are in fact one of the biggest parts of the shoe and could allow for a lot of modifications. However, so far, any study that has looked at the upper has either looked at it as an aesthetic aspect or from a comfort perspective. Now, this might make sense in this review since most of these studies were related to running, but and in running, the upper might play a smaller role. But what about other tasks? So other tasks such as tennis, which I have a quick video of here. I have a video of a point played between Nadal and Federer in the Australian Open. And in this video, I would like you to pay attention to the lateral movements that they're performing during the point here. And just to get a closer look at one of these side cut movements that these tennis athletes perform, I have a slow motion video of Rafa again. So just look at the angle at which he is landing, and he slides for a little bit at that angle. And then he gets ready to change the direction in a very short duration here. So just looking at these videos, we can see that the upper probably plays a bigger role than just comfort in a sport like tennis. The videos that we watched are not uncommon. These athletes change direction very frequently, and it is rare that they would use any traditional forward or backward movements to do that. Most direction changing steps are lateral or side to side in nature. And specifically, a study showed that more than 70% of the movements that the athletes perform are side to side during games of badminton, tennis, basketball, and similar sports. So based on these numbers, it may be beneficial to design footwear that can reduce loss of energy and make these movements more efficient for better performance. And one of the ways to do this may be by appropriately designing the shoe upper. The shoe upper may not only be important for performance aspect in lateral movements, but also for injury prevention. And here I have a video of Zion Williamson from a game where he actually blew out his shoe during a side cut movement.
Watch when he plants right here. His foot comes out of his shoe. That's unbelievable.
He broke his shoe with his own foot, but as you say, the injury.
So in this video, it is evident that these athletes are putting extreme forces during these cutting movements and direction changing steps on the upper and the side aspect of the shoe. So in order to improve performance and to prevent injuries, it is essential for these shoe uppers to be designed such that they can withstand these extreme forces. Even though the upper may have some key implications on athletic performance, only a handful of studies have looked at these effects in running. So these studies have found that stiffer upper constructions can result in lower loading rates, as well as lower peak plantar pressures during running. And the researchers that performed these studies speculate that these changes are potentially due to a reduced foot motion inside the shoe. And interestingly, similar studies have not been done for lateral movements, where we actually would expect the upper to play a big role. So the purpose of our study was to evaluate the effects of shoe upper construction on ankle joint work during cutting movements. And in this study, we hypothesized that a stiffer or a more structured upper would result in decreased negative ankle joint work. So we recruited 10 male and 10 female subjects to participate in this study. And our protocol included two tests. The first one was the maximum lateral shuffle test, and the second was the submaximal lateral shuffle test. So each participant performed the max shuffle test first in order to determine their maximum shuffling speed. And this test was followed by data collection in the submax test. Each of the subjects performed the submax test in 2 shoe conditions, which were different in their upper construction. So more specifically, we had a minimal upper and a reinforced upper. During the data collection, we recorded ground reaction forces as well as 3D motion capture data in order to quantify positive and negative ankle joint work. And the participants did perform the test in each condition in a randomized order. Here's a closer look at the 2 shoe conditions that we used in the study. So on the left-hand side, we have the minimal upper condition, which is a commercially available Adidas shoe called the Speed Factory. And it has a sock-like minimal upper made of white fabric. While the reinforced upper condition that we used, shown here on the right side, is the same shoe, but it has 5 synthetic reinforcement strips in the forefoot region in a crisscross manner. Now, these pictures make you wonder if these strips really reinforce the shoe significantly. And in order to address that question, we did some material testing to determine the stiffness of the strips. So for the material tests, we cut 2 samples of the same length and width from the 2 shoes. So from the minimal upper here on the left, we cut a strip of the white fabric from the forefoot region. And from the reinforced upper condition on the right, we cut one of these blue reinforcement strips also from the forefoot region. Then we mounted both of these samples in the Instron testing machine with sandpaper in order to avoid slippage. We performed 30-second tensile test at a strain rate of 0.2 millimeters per second. And from the results of the test, we found that stiffness of the minimal upper here in white was 0.69 newtons per millimeter, while the stiffness of the reinforced upper, or the blue strip, was 5.7 newtons per millimeter. This means that the reinforcement strips that were used on the shoe are little over 8 times stiffer than the white sock fabric. And we expect that having 5 of these in the forefoot in a crisscross pattern definitely makes the upper stiffer. Since the methodology used in this study is relatively new, I'll go over each part of the protocol before we go into the results. This test was actually developed by Philip Maurus here at the HPL, who did great work with varsity athletes in order to develop this methodology in 2019 during his time at the NIG lab. And in this study, Philip has shown that the test has good test-retest reliability, as well as the sensitivity to examine differences in kinematic and kinetics with footwear interventions. So the first part of our protocol was the max shuffle test, and the purpose of this was to determine the maximum shuffling speed for the participants. And the setup of this included a force plate on the right side and a starting point at the left of the participant. The distance between these points was standardized as we took 3 times the participant's leg length. Then to perform the test, the participants were instructed to shuffle to the force plate and back while taking 3 steps in the middle of the 2 targets. And these steps were in accordance with a metronome beat. Of the 3 steps, the first was either always on the force plate or on the starting target. So to determine the max speed, we had the participants start shuffling at a speed of 120 beats per minute. And once the participant performed a trial successfully, we increased the speed by 10 beats per minute. And we continue to do this till they can no longer keep up with the metronome speed any longer. Once they have an unsuccessful attempt, the speed is reduced by 5 beats per minute, and their last successful speed is considered their max speed. Here I have a short clip of the max test. So once we determine the max speed, we start data collection in the sub-maximum test. And this test is performed at 90% speed of the participant's max speed that we determined in the last test. So for instance, if a participant reached a max speed of 180 beats per minute, they would be doing this test at 162 beats per minute. During this test, we collect motion capture data and force plate data, and the setup included 8 cameras and 1 force plate. We mounted 17 markers on the participant's right foot and the lower leg. So on the foot, we had 10 markers, and these were mounted on the first, the third, and the fifth toe, the distal heads of the first and the fifth metatarsals, the bases of the first and fifth metatarsals, and lastly, the medial, lateral, and proximal heel. The other 7 markers we had mounted on the malleoli, epicondyles, and the shank. So the participants performed 5 trials in the submax test, shuffling to the plate and back 6 times, which gave us 30 steps for analysis in the 2 shoe conditions. The outcome variable of our study was ankle joint work, which was determined using the ankle joint power. And we calculated the ankle joint power as the dot product between the ankle angular velocity and the moments. This was done for 30 steps in both the minimal upper and the reinforced upper condition for all 20 participants. So here I've presented a mean power curve along with the standard deviations in the 2 shoe conditions, with the y-axis presenting power in watts per kilogram, and the x-axis is percent ground contact. The red curve represents the minimal upper condition, while the blue curve represents the reinforced upper condition. And from the graph here, we can see that there is a difference in the power curves of the 2 shoes. And specifically, if we look at the peaks in the reinforced upper condition, we do see that they are lower than the minimal upper. So next, we were determining the ankle work, which is the main outcome variable of the study. And this was done as the area under the power curve. So essentially, we took the area under this first half of the curve to be the negative ankle joint work, and the area under the second half of the curve to be the positive ankle joint work. Here we have a graph of the ankle work on the y-axis in joules per kilogram, so it's normalized to body mass. And on the x-axis, we have the different conditions for both the positive and negative work. Now we found that positive work was lower in the reinforced upper condition, which is represented by the blue bars here. We also found that negative work was lower in the reinforced condition, and both of these differences were significant. So positive and negative work was actually lower by about 0.07 joules per kilogram in the reinforced shoe. And just thinking about that number, it does seem small, but it is a difference of about 11%. Also, we can consider an average male with a body mass of about 72 kilograms, and we find that these differences are in the order of 5 joules. We compared these numbers to previous studies and found they are comparable to studies that looked at ankle work in other tasks such as running. So if we go back to the WhoCommerce study from 2019 that compared the ankle work in the Vaporfly to the other 2 shoes, they found very similar differences in positive and negative ankle work. They observed a decrease of about 8 to 10% in the Vaporfly. And if we consider the performance benefits of the Vaporfly shoe, we speculate that having a decrease in ankle joint work in the reinforced condition during shuffling may be beneficial as well. But we would have to do future work in order to test and confirm this speculation. We wanted to understand where the differences in the ankle work were coming from, so we went back and compared the different variables of the ankle power and work equation. So first we looked at the ankle angular velocity, which is here on the y-axis, and we found that peak dorsiflexion angular velocity was significantly lower in the reinforced upper condition, and the difference was about 12%. So previous studies have shown that higher joint angular velocities actually come from faster shortening of muscle tendon units, and that further comes at a higher metabolic cost. So if reinforcing the upper decreases the dorsiflexion velocity, it may be that the muscle tendon units also shorten slower during the touchdown phase. And further, we speculate that braking in the reinforced upper condition may have a lower metabolic cost due to this. But this speculation should also be tested in the future, as it could have implications on performance in the sports that require frequent direction changing or braking and accelerating. Next, we also looked at ankle peak moments in the two shoes. And we found that the ankle moment, which is here on the y-axis in Newton meters, was significantly lower in the reinforced upper condition compared to the minimal condition. This is a difference of about 9%. The last variable that we looked at was stance time in the two shoes, and we found that the stance times in both the touchdown and the push-off phases were significantly shorter in the reinforced shoe. Now, this decrease in stance times may also be quite beneficial to athletes since they may be able to change direction faster in the same task. So to summarize all the results that we found in this study, we saw that reinforcing the upper results in decreased negative and positive ankle joint work. It also results in lower peak dorsiflexion velocity at the ankle, as well as lower peak ankle moments. And lastly, stance times are shorter in the reinforced shoe. We believe that these results indicate that reinforcing an upper can provide performance benefits in lateral shuffle movements. And lower positive and negative work suggests that the athletes may be able to perform the same task with a lower energy cost. So based on these results, the upper does seem to play an important role in these movements. And we believe that appropriately modifying or designing the shoe upper can have beneficial outcomes for lateral shuffle movements. There were some limitations in our study. First, the footwear conditions that we used were primarily running shoes, and these are different from shoes which are specific to sports involving lateral movements. But the reason that we chose these shoes is because they systematically differed in only one aspect, which is the upper reinforcements in the forefoot region. And since this was the first study looking at this, it was important for us to control for any other aspects of the shoe in order to make statements about the upper stiffness. The other limitation in our study was the marker set that we used. If you recall, we only used the marker set up to the knee. And for this reason, we were not able to quantify the work redistribution during the task. And previous studies have shown that lower limb joint work can be redistributed as a result of shoe interventions during running. So further studies that examine the lateral shuffle movements should address this with a larger marker set and try to answer whether we see a work redistribution in this task as well. We collected a lot of other data during this project, including plantar pressure data and EMG data. So currently we are starting our EMG analysis in order to compare muscle activity in the two shoes. And I look forward to sharing more results from these analyses in the future. For this project, I would like to thank my supervisor, Dr. Benno Nig, as well as Sandro Nig for providing the support and funding for the project. I would also like to thank Eric and Sasha, who were co-authors on this project, for their help throughout the analysis. As I mentioned earlier, this project was part of my undergraduate studies, and Dr. Darren's definition was the instructor of that course. He provided great feedback and guidance, so I would like to thank him for that as well. And lastly, I received a scholarship from the program for undergraduate research experience based on this project, so I would like to thank the university.
Thank you very much, Ashna. I really enjoyed your talk. So if you could now unshare your screen so we can see everyone. Thank you. Also, I would like to kindly encourage everyone to turn on your camera if you are okay with it, because I feel it is always good to see each other during the discussion period. Thank you very much for doing that. So if you have any questions for our speaker, please use the icon raise hand button, which is found if you go click reaction icon at the bottom of your Zoom screen. Now the floor is open for the question. So actually, let me start asking the question, Ashna. So I'm not super familiar with this research field yet, but I'm just curious so you saw the difference between the two shoe at multiple variables. So I'm just curious, how is the decreased work related to better performance and injury prevention? Because that's what you mentioned as one of the part of the significance in your study.
Right. So I would just like to make a point about the injury prevention, even though I did show a slide. For this project, we only focused on the performance aspect. So with respect to the ankle joint work and the decrease that we did see in the reinforced shoe, based on previous research, we speculate that a lower work at the ankle joint can result in a lower, or can relate to a lower metabolic cost of performing the task. And because these athletes in these sports are performing this movement repetitively for a long duration, we think that minimizing the work at the joint can result in that metabolic cost over that whole duration of the game.
Thank you. I see Arash, you have a question for Ashna?
Yeah, great presentation. I was wondering about this. What do you think the cause of this increase or decrease in the positive and negative work is? Is it because of the change in the center of mass excursion while shuffling from one point to another, or is it just a redistribution of the joint work?
So I cannot answer that question specifically since we did not quantify the redistribution, but I can speculate based on the previous studies. So one of the reasons that we think there was a change in the reinforced upper is because of less relative motion inside the shoe. So even previous studies speculated that when this upper is reinforced, there is less movement inside the shoe. And that might be relating to these biomechanical differences that we are seeing. But again, it could also be because of that redistribution, and to confirm that, future studies, or we can do more studies to confirm that speculation.
Okay, thank you.
Actually, I also have a more question. So I'm just to start keep thinking. So you compare the two different shoes, and the reinforced shoe had like more stiffer material attached along the cover part of the shoe. So do you expect that you will see the same result or a big greater difference between the two shoes if you are using more reinforced shoe material? And do you also expect there is a kind of ideal amount of the reinforcement in the shoe, so that if you go a little more higher level of reinforced level in the shoe, then you will not actually see improved or better results?
Right. The first part of your question with the strips that we had in the shoes there are only 5 strips, and it is less reinforcement than you would expect. So for that part, we definitely think that with even such a small difference, we saw these biomechanical changes, and we think that more appropriately at stiffening the upper will actually can result in bigger performance benefits. But then that also comes back to that optimal point. And yes, I do agree that there may be this optimal point where if you make it way too stiff that your foot is not even able to change its shape to perform the task, then it could be detrimental to performance. But I think it would be an interesting study in the future to take very stiff shoes and try to find that optimal level.
Sure, thank you. I see Brent, you have a question?
Just quick clarification. So with the stiffer upper, you have reduced moments, reduced velocities, and reduced powers. And then what happened with the contact time?
So contact time was also shorter in the reinforced upper.
So that's quite puzzling, isn't it, to me? I would think that, it's a bit of a constrained activity, and if you're doing less work, you're going to have to maybe increase the contact time in order to perform the movement. I think that's puzzling to me. Were you surprised by that finding?
We were, yes. And one of the questions that came up a lot in the review process of this paper was if there is a decrease in the stance times, then isn't that worse for performance? But for that reason, we went back and looked at these angular velocities, and the fact that the plantar flexion angular velocity did not change kind of suggests that even with a shorter time, they're generating those same push-off forces. And that's why we speculate that having this shorter time of push-off and stance time can be beneficial for the performance. It is puzzling, and we would need to do more research on this to be able to understand these effects.
Because it means that the impulse is less for the stiffer shoe, I would think. Lower moment, lower contact time.
Correct.
So I don't know, to me, I would think that that would be a hindrance to performance, but.
So one of the things that was interesting is that we didn't even see a difference in the net work. So the net work, they're still able to do the same amount of work with a decrease in positive and negative work. And secondly, that was the same question that kept popping up, that isn't it a hindrance to performance? But they are able to perform the same task, and they're not getting slower or not able to keep up with that metronome in the other shoe.
Okay, all right, yeah, okay, so network is the same.
Right.
Okay, thanks.
Ian, please go ahead.
So one thing that I'm curious about is the role of lacing. So presumably how tight you've got the shoes tied up is going to have a big impact on the stiffness of the upper. And I'm wondering how you controlled for that, and if there might be systematic differences in how tight the laces were between the different shoes, which might have explained things. So how did you control for lacing, I guess is my question.
So in this project, we didn't really control for lacing. We instructed the participants to lace as they normally would for a task such as lateral shuffling. So the participants did their own lacing, and I guess we didn't really control for that. But again, we expect that they would lace the two shoes similarly when they're about to perform the same task. Now, if this study happened during COVID times, we'd be lacing up their shoes, and that'd be a better control. But for now, they did that on their own.
So I guess a lot of that could be just how comfortable, if it's left to them, it might just be how comfortable the tightness of the lacing is. So you might not have such big differences between them. Or maybe the laces might have been a little bit looser on the reinforced shoe relative to the other shoe. So.
Sorry.
No, so if you're to do this again, maybe do it with a shoe that doesn't have laces. That would be just something that I want to see pursued in the future, just to control for that uncontrolled variable.
That's actually the point I was getting to. So one positive thing about these shoes was that their sock-like upper is very tight, and essentially it doesn't even need laces. I think the laces are just there for the fact that you can make them tighter. And most of the participants complained about the fact that it's hard to get these on. And so while lacing, they weren't going a lot tighter. So even if they were very loose in lacing the shoe, the upper was stiff and snug enough that it would still hold on the same way in the two shoes.
Both shoes, they complained about not getting them on easily.
Correct.
Okay. Thank you.
Yeah.
Yep, Emily, please go ahead.
Hi, Ashna, nice talk. You mentioned that some of your results are influenced by the foot's relative movement within the shoe. Can you just clarify for me, because you are tracking markers that are placed on the outside of the shoe, kind of which of your variables are capturing the relative movement of the foot within the shoe, and which of them are just capturing the outside of the shoe and how that movement changes due to the stiffness, if that makes sense?
Yeah, for sure. I'll say that in this study or in this analysis so far, we were not quantifying for that relative movement inside the shoe. So all the markers that we used for this ankle joint work, I don't think they can really tell us much about the movement inside the shoe. In the future, we do have some PEDAR data, and maybe somewhere in that data, we'd be able to see if there's more movement. So if there is more movement and the foot is sliding laterally, I would expect to see higher forces or pressures at that lateral aspect of the foot. And if there's less relative motion, I would expect to see a more even distribution of the plantar pressure in the shoe. But for now, we didn't really quantify the movement. It's just speculation.
Thanks.
Yep, I see, Walter, you have a question for Ashna as well.
Sure, yeah, very nice talk, Ashna. Thank you. I had a couple of questions. First of all, especially when you were talking to Brent and you talked about work and impulse and that type of stuff, am I correct in assuming that you always refer to the power and work at the ankle joint? Is that correct?
Correct.
Okay.
Yes.
So then, and I was actually equally puzzled a little bit like Brent about the result because, well, yeah, for a variety of reasons. But let me ask you the crux question here. Did you actually check whether or not the frequency at which they hopped, but if the speed at which they landed and the speed that they left the platform was the same in the two conditions? So the entire work required, was that the same for the whole system? Because my understanding is, if I can elaborate a bit, that you controlled like for that they went in a certain rhythm, you know, like 180 pulses per and that type of thing. But really, that's not really important. You know, what's really important is when they landed on the platform, when they went off the platform, what was the speed, and was that the same for the two conditions?
Right. I don't think we looked at that in our analysis right now. The idea was to go back and look at that angular velocity to understand if it's changing in that push-off phase and the touchdown phase. And we did see the differences in the touchdown phase. But with respect to the velocity exactly with which they were landing and leaving the plate, one was not controlled. Only the speed with the metronome was. So yes, I think it would be interesting to look at that in follow-up analyses for this and try to answer those questions.
Yeah, because, you know, let's say if I'm going, I have no idea how fast they go, but let's say I'm going with 5 meters per second right on the platform, is 5 seconds off the platform, then, you know, according to impulse momentum or the work energy principle, I would have to exert exactly the same impulse or exactly the same work on the entire system. And some of that would come from the ankle joint and some from the knee and some from the hip and so. So if you had less at the ankle, presumably you would have to have more on the other. But since you have less, you know, you have a lower ground reaction time, you have less work performed and everything, it almost suggests that maybe they did the movement that they landed and went off with the one shoe a little bit less fast than with the other one, and then maybe in the middle couple of steps made up for the speed, so to stay on rhythm. So I would very carefully look at that. And of course, you can easily do that because you have the ground reaction force. So you can just look at the lateral impulse and the ground reaction force, and then you immediately know if that would be the same or not.
Correct. Yes, that's right. And future analysis can help us answer some of these questions for sure. And I would be interested in looking at it because for now, it just suggests that it is changing this, and it could be because of multiple different things that are happening in that shoe.
And the other thing that I was wondering was, you know, you said if they needed, you know, less work there at the ankle or less power at the ankle, then that might be associated, you know, with less activation of the muscle, and you save muscular metabolic energy. And I was wondering, because especially in that one film there, the Nadal video that you showed, that was a lot of, it's not really flexion, but a lot of movement in the ankle. And I wonder actually how much of that is taken up by the muscles and how much by the ligaments. And so I was wondering if you tried to force the ligaments, well, the ankle into the type of positions that you observed, and then realized, how much of that, these extreme ankle positions would actually be taken up by passive tissues. And maybe all you see is really passive, is done by passive tissues, or mostly by passive tissues. And so if you have more or less work, you just stretch your ligament 1% or 2% more, but it has nothing to do with muscular work. Did you ever try to look at that?
That was the plan with the future, the next part of the study with the muscle activity as well, and to look at the muscle activity and try to understand if the muscles are actually working less in this case in the reinforced shoe. But I will definitely keep your comment in mind, because it definitely is an interesting part, that if we force the ankle in those positions, is it making a difference in those passive elastic structures?
I have this more a comment, but I've performed 3 sports that I can think of where I didn't want to slip in my shoes. And one is climbing, and the other one is track cycling, and the other one is running on the track. And in all these events, I always used shoes that were actually slightly smaller than really comfortable. And I didn't wear any socks at all. And so I was wondering, and and then you can go, of course, even further in track cycling. The people don't go into the shoes, and then the shoes are clipped onto the bicycle. But in fact, the shoes in track cycling, especially for the sprint events, they are directly bolted to the crank, to the pedal, and so I was wondering if something could be done with the sock shoe interface that might potentially reduce that, like half thinner socks so that the shoe is comfortable and there's not as much room there, or maybe even that, I don't know, the sock is glued into the shoe so that there's no slippage between the sock and shoe, or any other aspects of it. Just as a comment.
Yeah, for sure. There are so many possibilities to modify this, and like these sports, you want to minimize your shoe slipping, because I actually injured myself because of that. I was wearing a size too big, and I got a hairline fracture because of my foot just moving while playing tennis. And so that was exactly the point of trying to understand if we can affect this by modifying the footwear features.
And talking about tennis, because I've never played tennis, in tennis shoes, are they do they end below the ankle, or do they go above the ankle?
They end below the ankle.
Below the ankle. And in basketball, I guess normally they would go above the ankle. Is that correct then?
Correct.
Okay. And in tennis, you have it below the ankle because you're more worried about speed than support, or what's the reasoning there?
I think that might be one of the reasons that you need more speed. And the other thing there is, I feel like there is more distance that you would cover in one bout. So in basketball, there is very little distance covered in one movement, but in tennis, you still want that option to be able to run forward or backward and have that mobility.
I was just wondering, I'm sitting here, I'm not a shoe designer, but what about a shoe that would look, of course, really ugly and would be really awkward, but a shoe that had an extension that would really hug your lower limb with an elastic material. So you had a shoe, and then you would have that sock that's attached to the shoe would go over your ankle and up like a sock, but it's very elastic, and so you would take up a lot of the energy through that elastic material if your ankle went into a very strange configuration, like in tennis or basketball.
Yeah, that's actually something which is commonly seen. They wear this ankle support or a brace when they are going into these weird positions. So definitely including that in a shoe could be beneficial, but again, we'd have to see how much of a benefit that actually provides.
Well, it sure would look ugly, but it might be functional.
It might be
Thanks.
very functional, especially to avoid these injuries that these athletes have. So taking all the notes for follow-up studies.
Thanks.
Ashna, I also actually got a question through a Zoom chat as well, so let me just read it for you. If it is shown that work distribution can be redistributed to the other joints, why did they not use a larger marker sets?
That's a good question. We initially wanted to look at the MTP and the ankle joint work. And for that, we thought that this marker set was sufficient. And the main reason that we looked at the ankle joint was because we thought that it is directly in contact or the closest joint to these reinforcements that we have on the second shoe. So as a first study, we wanted to look at the joint that is closest to this and would be directly influenced by these modifications. But between and during the study, we realized it would have been helpful to include a larger marker set. And in the future, we do plan to do that, but it was slightly late to include that.
Great, thank you. I see Art, you have a question for Ashna?
Yeah, I just want to echo some of the other questions that were about, what is happening at the other joints or the whole body. And I think that's a really interesting question. And I guess I'd like to offer a possible interpretation of one of the other possibilities. So I guess, one of our first possibilities is just to think, okay, people are doing essentially the same task as far as their body is concerned, but then they're doing a different amount of work at the ankle under the reinforced condition. And then the question is, so what's happening? Is there a redistribution or something like that? But then the other possibility that I think people have been asking about was maybe they're really doing a different task. And then first of all, what would they be doing differently? And then what does that mean? And I guess I just want to suggest a possibility that if they are doing something differently, one way to do that is let's say that in a reinforced shoe, you have a more secure way of stopping. So let's say you can use the coefficient of friction more to its fullest. And then what you could do then is when you're changing direction, it should be possible to basically get away with moving your center of mass less. So I think that is a possibility, is that they literally are doing less work. Do you call that the same task? I'm not sure whether you would call it the same task or not, but the idea is you're fulfilling the duty of of what's being asked of them, and then they're doing that with less work. And I think that is a sensible thing for someone to do. When you do a shuttle run, people don't usually move their center of mass all the way over the line for the shuttle run. They move their center of mass less, and then they stick their foot out, and then they're using, they're trying to get as much horizontal force as possible, which is helping them not move their center of mass as much. So I wonder if that's what's happening. And then there's the question of the interpretation of that. And I guess my interpretation is that could still be a valid and helpful thing for the shoe, is that it lets you do, outwardly the same kind of task, but in a way that saves your body a little bit of work. Although that's still an interpretation. We're not sure whether the less work really helps the person or not, but I think it's a possible interpretation. But I think it would be really interesting if that's what happens, is that people know to take advantage of a, quote, better shoe and do less work with that. And as long as they're fulfilling the overall task, I think that could be a good thing.
Thank you, Art. Thank you for helping me out with that interpretation. And that was exactly our interpretation as well when we had all of these similar questions come up in the review process. And we said the exact same thing, where they are able to do the same task with lower work right now. And obviously trying to understand where that is being compensated, and if it is being compensated, we would need to test that further. But I think it's still a good result that they are able to perform the same task and they're not compromising anything in the performance of that task, but still lowering this work requirement.
Yeah, and I guess maybe a general comment on experiments is that I always like to be greedy, even if it causes extra pain. So I think the problem here is that putting on extra markers is painful for the experimenter, at least. It takes more time. You get, for your amount of time with your subject, you're spending more of it basically wasting time. But I am in favor in general of putting on markers even for things that you're not that interested in. So, a lot of times people do locomotion where they'll only put markers on one leg. But I feel like if you can at all afford to do it, I'm in favor of putting more markers on than you think you need, because then it helps follow up on these kinds of questions.
That was my biggest takeaway in this project. It was my undergrad project, and I was glad that before I entered my master's that I learned that fact, that always collect more. You can go back and look at everything that may be able to answer that question. And I'm definitely applying it now. Thank you, Art.
Would there be any other questions for Ashna? If not, I would like to thank Ashna again for giving interesting talk. So next week's seminar, we'll be hearing from Nada Ghazaleh, and she'll be talking about the effect of oligofructose fiber supplementation on knee osteoarthritis progression in obese rats. I hope you enjoy the long weekend, and I'll see you all next week.